Beep. All right. Yeah. Okay. Well, I hope you're not yet asleep. So it's going to be the next half hour is just going to be about some specific features of Kepler and some specific features, especially in CUDA 5.5. I put it 5 here. The biggest change between 5 and 5.5 is actually that something that used to be just available on Cray systems now works on pretty much all the different platforms. So in the early days of CUDA, the main goal was always just to get raw performance out there, and it was pretty much still figuring out how people would want to program these devices. But now, given that we have some 5 or 6 years experience in how people want to use these devices, programmability becomes increasingly an aspect that we care about and that we want to focus on. And so one of the design goals of Kepler was not only to provide huge performance and be very power efficient, but also to allow relatively easily to develop code for GPUs. So one of the things that we found out by looking at other applications was that there was a whole range of problems that were inherently difficult to do efficiently on previous generation GPUs. So one thing was there was no mechanism for calling libraries from within kernels. Actually, for a long period of time, it wasn't even possible to call functions from within kernels. Even though you had the mechanism of labeling a function as device, and so structure your program slightly more efficiently, it all just got inlined, and it wasn't a true function calling mechanism that happened on the GPU. So that was from a software engineering point of view was a necessity. Simplifying this whole divide between the GPU and the CPU, these separate memory spaces, that's another kind of a sticking point that people complain about a lot. So that was something that needed to be addressed. The other thing is that GPUs are getting wider and wider and wider. Actually, in some cases, we even drop the clock rate down, but make them wider. So from Fermi to Kepler, the core clock went down, but we added more processing elements, and so net got a speed up. But that means that your application actually needs to be able to exploit all these parallelism. So in Fermi timescales, you probably had to use something like 20,000 threads concurrently, maximum. So the device could handle 20,000 threads. Now we're closer to 30,000 threads that the device can handle. So there should be a way of making sure that all this parallelism that's available can be readily exploited. A lot of problems simply don't exhibit as much parallelism. So there has to be some added, something that helps you using the GPU efficiently, even with smaller degrees of parallelism. Dynamic load balancing, right? It's with this rigid mechanism that the CPU calls out and generates work for the GPU, and the GPU then just crunches along and comes back to the CPU, and then you fire off the next part of work. That's just difficult to do any kind of highly dynamic things with such a programming model. That includes then data-dependent execution and recursion. And so this all boiled down to this notion of the dynamic parallelism. So what does that mean? I mean, lots of nice terms, but at the end of the day, it simply means that the GPU can generate work for itself. So in previous generations, it really was constantly a kicking off of the GPU, all driven by the CPU. And now with Kepler, you can do that from within the GPU as well. So here we have just a kind of a timeline for whatever, some operation. A typical use case would be, for instance, an LAPACK routine where you have like batches of dense linear algebra that you need to do, but then you have to do some pivoting again, so you need to look into the elements that you need to figure out if you have to, you have some data dependency, and then you're doing a lot of parallel work again. In previous generation devices, this meant that, yeah, the CPU had to go and kick off some work on the GPU. GPU reports back, and the CPU then instructs to process more things at the same time, and so on. So first of all, we see that we have a lot of transitions between host and GPU. And secondly, we see that a lot of the GPU resources go unutilized, simply because we don't have sufficient parallelism for many of these steps. Now, with the dynamic parallelism, first of all, we don't have to go between host and GPU that often. Remember, that's the PCI Express bus. That's not particularly powerful. And so we can remove that bottleneck, and we can now better utilize the device, because some of the work might just depend on, could be executed concurrently that previously was serialized, simply because we had to do the decisions from the CPU side. So this all looks fantastic, and I mean, one typical use case for this would be any kind of adaptive mesh refinement algorithms, like in fluid dynamic, stuff that people have actually accomplished to do in the old way of describing, and but it would just be much more convenient if the GPU could make the decisions by itself. How does that look like? So when you when you look at the conventional CUDA program, like down here we have the host program that calls the parent kernel, and you're now all experts in CUDA. So this means we're launching a single block and just a single thread within the block. So we're launching this kernel. That's nothing new. And then in the parent kernel, now suddenly we have a new element, which is that we now have this triple bracket notation inside the kernel as well. This is dynamic parallelism right here, that you're launching a kernel from within a kernel. Actually, you're launching an entire grid. So in this case, you're launching one thread block with 10 threads of the kernel child kernel, and this child kernel just as a printf. So the output of this will be, well, this guy goes into the parent kernel. This one launches 10 children, so it will be hello from 0 to 9. And then there will be a world, and this will be the result. Then the application terminates. Yes? Yes. Yeah, I mean, you can do this recursively, but the one thing to keep in mind is in real cases, you will hardly ever see it in such a blank form, because usually you're not launching a single block, single thread grid. And so what happens is that every single thread will launch a new grid. So you can quickly create massive amount of work. Just imagine here you have whatever, 100,000 elements, 100,000 threads that you're creating here. And each one of these 100,000 threads now creates another 100,000 threads of the at the next level. So this can quickly fill up your device. The pattern you will more likely see is that there is some conditional here saying, if thread ID is equal 0, then launch now this extra work. Now there's a few things to look at, right? You see all these device synchronized parts in here. So the execution model within kernels that are being launched from within kernels is the same as on the host side, namely that the child kernel is executed asynchronously to the parent kernel. Now, we're not saying anything about when exactly it will be executed. We're not saying where it's being executed. All we're saying is that it will eventually get executed. And it will be executed once you hit, for instance, a device synchronize. So at the point when you hit a CUDA device synchronize, you're guaranteed that all the work that has been done before, or that was launched before, has also completed. Well, once you go beyond the device synchronize. So this is then a barrier for your entire, for the kernel, for all the grids that were launched within this kernel. So, for instance, that then heavily depends on the available resources. If, for instance, in this particular case, given that we're just launching a single block and a single thread, well, this will sit on exactly one SM. So we have, on a K20, we have 13 SMs that are not utilized. So at the point when these children get launched, there's a certain chance that they will actually start executing on the additional SMs that are available. What do you know? But on the other hand, it could also be that if the device is already fully packed, that the execution will be serialized, that the parent kernel will continue until you hit the device synchronize, then it will move the children kernel onto that device, onto that SM, and continue working on the children until they are all completed, and then go back to the parent. So you cannot assume any order of execution of the individual kernels that are being launched from within kernels. I hope that makes somewhat sense. Again, there was a lot of effort being made to make the syntax basically identical to the syntax that we have on the host side. So the syntax for the kernels is the same as the syntax for the on the host side. So the kernels now can also do things like mallocking memory. We even have parts of the cuBLAST routine that can be called from within kernels. So that's just an ecosystem we were slowly building up, and we're also trying to figure out who wants to use these mechanisms. But if you have an application that is probably not fully utilizing the GPU, doesn't exhibit as much parallelism as you would need, and if you have a lot of data-dependent execution or control flow, give it a try. We certainly would be very interested in seeing more use cases of the dynamic parallelism and how people want to use it, just to help us guiding also what needs to be developed, where to place the focus for future development. Now, by default, this mechanism is not turned on. So in order to get access to it, you have to specify one additional flag when you're compiling with NVCC, and that's -RDC, which stands for relocatable device code equals true. Yes? Right. Did you specify the -arc equals SM35 when you compiled it? Nope. I told you this morning that you should, when you compile NVCC, -arc equals SM35. Right? Again, it's the fact that by default we're compiling for SM11, which is an ancient version of the architecture, and yeah, dynamic parallelism is only available on SM35. Might be on SM30 in general, but yeah, I think it's actually SM30 is sufficient. But so if you're then trying without SM35, it will just complain that it's not available. Did you try it with SM35? Oh. Oops. Yeah. Come on. So there's the NVCC ---- help that can, oops. NVCC minus minus help would give you the information if we had the right module loaded. And now we have it loaded. And so you will see, oops. Oops, there it was. Now I can't go back. But anyway, you get the point. Manage archive auctions here. Yeah. So here we have the minus minus arc. And you see all the different forms of architecture that you can specify. Right, yeah, and it's wrong. It would be minus minus GPU dash architecture or minus arc. Yeah. But yeah, and then the other one was that we had here was the RDC, right? So which is the relocatable device code. And so this is the part that you need in order to have dynamic parallelism enabled. So one thing also, and we might need this later on, we also introduced a true device code linker. So in previous generation of NVCC, you basically had to have all the code that was targeting the GPU to group that together and compile it once, and you had one monolithic part of the device code. With CUDA 5, we can now link together individual pieces of device code. And so there's a bunch of additional flags that were introduced. Again, the goal was to be as close as possible to the compiler flags that you would expect from the host side. So the first one is if you just want to create the object code and not continue then with linking, I mean, on the host side, you would use the -C flag, right, to compile only, but not to link. That's why NVCC now introduces the -DC flag. That's for device compile only. So in that case, it will compile the device code, but not try to link it afterwards. So this allows you to make basically object files with device code embedded. But then when you then want to build the application, you actually need to link those guys together. And for that, you have the option -D-link. That's to call the device linker. So in this case, we're taking the A.O and the B.O, and we assume that both of A and B contain some snippets of device code. And with this operation here, with this invocation of the device linker, we will now create an additional object file, link.o, that contains the linked together device codes. And then in the last step, we want to link the object files both for the host and the device. For this, we just use the host linker. And we create the output file, in this case, A.out. So this is if we want to use, if we want to break our compilation into multiple steps. Now, the same thing happens if you have dynamic parallelism embedded. The only thing you need to keep in mind is that we now might have function calls from within the kernels, especially function calls to the runtime library, like you can do CUDA mallocs from within a kernel. That's why at the link phase, we also need to link against the device version of CUDA RT. So we have a special library called CUDA dev for device RT. So that's the CUDA RT, the runtime library with device code. So you need to use that both at the time of device code linking as well as at time of host code linking. Yes?
Could you specify again why one needs the second step?
The second, so let's look, yeah, so the second step here Let me check if I have a slide. Nope, I don't have it here. So I need to do hand waving. Right, basically what happens is, think about it this way. The host compiler doesn't know anything about device code. Right? Device code to the host compiler is just a chunk of text that is being embedded in your object file. So if you want to modularize your code and you want to build, for instance, device code libraries, you want to have a piece of device code device object code, and you want to link this against your other device code. So at one point you need to have a linker that links the device object files together. This is what we do with the second line. So here, at the first line, we're saying we have two pieces of code, two source files. Both of them contain host and device code. Okay, that's just an assumption. I probably didn't mention that, but so both A and B.cu, they contain host and device code, right? And so with the -dc, we create object files, and so A.o contains both object code for the host as well as object code for device. And then with the second line, we just link together device pieces of code in A and B, and we create the linked version of that. And then finally, we use just the host linker to get the host pieces of code linked together, and we link in the linked part of the device code to create the final binary. Now, the piece that makes dynamic parallelism work is as follows. So what you can, again, a very abstract sketch of the device might look like the one on the left-hand side. This was the Fermi generation, the previous generation of devices we had. Basically, on the GPU, you have a piece that is responsible for just handing out work to the individual streaming multiprocessors. Right? You remember that on each one of the streaming multiprocessors, we can have multiple thread blocks that execute at the same time. Well, we can have way more thread blocks than fit on any one of the on all of the streaming multiprocessors at a given time. So let's assume that each streaming multiprocessor can hold 4 thread blocks for our particular kernel. So it would be 4 times 4. 16 thread blocks can be actually dispatched onto the SMs. Well, if we launch a grid with 100 thread blocks, well, they will all be sitting in the work distributor that has, waits for the active thread blocks to complete, and then put the next one onto the SMs until all the thread blocks have been executed in your of your grid. Now, so this was a true push-forward architecture. Now, with the GK110, the SMs now can spool back work to this grid management unit. So it can put a new grid of work onto that unit. And this one will then be given to the work distributor, and it will hand out the work to the individual streaming multiprocessors. So that's the part that enables dynamic parallelism. Now, as you can see, there's another part here, which is this single line that comes from this stream queue management. We will talk a bit more in detail about streams tomorrow, but think of streams as individual pieces of dependent kernels that can get launched. Right? So you have a few operations in sequence that need to be processed. You want to put them into the same stream. Now, you could have another set of operations that need to be processed in sequence, but are independent of the first set of operations. So you could have 2 streams, and they can be executed independent of each other, as long as the order of the operations within a stream is maintained. Now, this can help you to better utilize your GPU, because again, if you had a kernel that only uses one SM, well, there might be another kernel launch in another stream that could be dispatched onto the device at that point. However, the architecture of Fermi didn't allow the work distributor to have access to all the individual streams at the same time. And so it was very easy to confuse them, and which led to false serialization, so that in theory, work that could be possibly executed concurrently was not executed concurrently. This is now fixed in GK110. And the biggest benefit here is that, this grid management unit has now access to all, or to a large number of streams, and can pick the one that's most appropriate at any given time. And the biggest benefit here is in cases where, for instance, you want to share the GPU amongst multiple MPI ranks. So let's look at this in this example. So for instance, we have an MPI application, and on a single MPI rank, we have the following work. And this workload consists of a part that in theory could benefit from GPU parallelization. So something, for instance, that's embarrassingly parallel and would work very well on the GPU. And then we have a part that cannot really benefit from the GPUs. For whatever reason, it would be parallelizable, but it just doesn't fit there. And then we have some inherently serial part. Well, if we go to just multiple CPU ranks, or just use multiple CPU cores, what will happen is that, oops, no battery, okay. Well, what will happen is that both the part that's potentially GPU parallelizable, we assume that it also is parallelizable on the CPU, that one shrinks in half when you go from one processor to two, and the CPU parallel part will also shrink. Okay, that's a fairly straightforward scaling here. Then you go to 4 and to 8. By the way, for instance, one reason for having a part that's CPU parallel only is because it's a large code base, and so far you've only touched part of the entire code base, and some part you haven't moved to GPUs yet. So that would be a typical part of your blue bar. Now, when you now go to GPUs, well, the yellow part, the GPU parallelizable part, will shrink tremendously, right? Because, yeah, it has been accelerated with the GPU, and that's a part of the application that can be accelerated with a GPU. The CPU parallel part, the one part that you haven't moved to GPUs yet, will remain exactly the same, because you're still using just a single MPI rank. Now, what HyperQ allows you, or the MPS allows you, is now to split the GPU amongst multiple MPI ranks. So the benefit is that you will also see, you can use all the CPU cores that are available, which helps you shrinking down the parts that are not GPU accelerated. And on top of that, you're also seeing that the part that is GPU accelerated will shrink as well. So this feature, as we call it, MPS, it used to be called proxy, has been renamed to multi-process server. That's this technology that basically allows you to share the GPU between multiple processes or multiple MPI ranks. And the benefit of that is that you can both take advantage of all the CPU cores and therefore get the speed up of the CPU parallel part, and you also get the benefit of the GPU acceleration. And just as an example, what this meant for a code called CP2K was that right before we had proxy, or before we had MPS available, we were limited to one MPI rank per GPU, and so we got the lower scaling graph, so up to 16 nodes, we only got a speed up of about 6. But then, because we had still a fair amount of code that was not moved to the GPU, And so by limiting ourselves to a single MPI rank per node, we had, we still had a lot of work that couldn't take advantage of all the cores that we had available on the CPU side. With MPS, I still use the old term proxy in this graph. With MPS, we now see both the CPU acceleration as well as the GPU part acceleration, helping us to get big speed up. So, long story short, what do you need to do for that? Or when do you want to use it? You basically want to use MPS in cases where you have only done parts of the work. So you have an MPI application, and you have only ported some part of the code to CUDA or to OpenACC. And you still have a bulk of the work that needs to be done on the CPU side. In those cases, there's a certain chance that MPS will help you. There's no application modifications necessary. Basically, what you need to do is you have to have an additional process that's running on each node. On systems like 30, this is done transparently to you. The job scheduler basically takes care of it, or I'm not even sure. Most likely, it runs persistently on those nodes. All you need to do is to set an environment variable, cray CUDA MPS client equals 1, and at that point, you can share the GPU between multiple MPI ranks. So this is another one of the add-ons that in CUDA 5 was exclusively for Cray. In CUDA 5.5, it has been opened up to all the other platforms as well. So with CUDA 5.5, you have access to the proxy to MPS, from all platforms. Okay, for optimizations for Kepler, just a few things to keep in mind. First of all, if you have code that was compiled for Fermi, it should just run on Kepler, as it is. However, if you want to get access to the new features of Kepler, we come to those in a second, you want to recompile, and in some cases even retune some of the bits of the code. This is simply because we have some additional instructions that you can take advantage of, and so the compiler, you need to recompile it so that you can take advantage of these instructions. What are these instructions? So there's basically 3 classes of optimizations at the instruction level that happened. Probably the most beneficial one is the atomics. Right, when you're writing parallel code, you always have to be looking out for potential race conditions. Right, that you have multiple threads that try to modify the same variable in memory at the same time, and you would end up in an undefined behavior depending on, or in a behavior that depends on in which order that these operations were executed. And that's oftentimes not what you want to get into. So there is a mechanism for making sure that you have not 2 threads that write to the same location at the same time. Those are so-called atomic memory operations. And so it used to be, again, in Fermi, it used to be that atomics were very expensive. Basically, whenever you tried to do an atomic, it locked up the entire memory system, and you ground your application to a halt. This is now completely fixed in Kepler, and the overhead that you're incurring with atomics is, it depends on the exact circumstances, but it can be just as little as some 30% or so overhead. So this tremendously simplifies the design of algorithms, and I'll have an example in a second. The shuffle instruction is another interesting one because it's another way of communicating between threads other than going through shared memory. And then there's some bit level stuff that I'm not getting into details. So let's first look at the shuffle instruction. Basically, previously, when you wanted to exchange data with your neighboring thread, what you had to do was we both write, or one thread writes its data to shared memory. Then you have to have a synchronization, and then the other thread loads this value from shared memory. So you had a full round trip to shared memory, and you had to have a synchronization in between. That can be relatively expensive. Now with this new shuffle instruction, you basically can, one thread can say, I want to grab the value that sits in my neighboring thread, or a few threads over. And so there's various different patterns that you can exchange data with adjacent threads. So shuffle can be a very powerful mechanism when you need to exchange data on a fine, on a fine level. One caveat, it only works within a single warp. So it's not within an entire thread block, it's only within a warp. So only a chunk of 32 threads can directly access variables that sit in a neighboring thread. Jumping over those, yes? The question is where would the atomicity come into play, right? So shuffle is really just an exchange. It's not, you're not performing an operation on it. It's not a reduction. And so there's not actually a need for atomicity. However, you're right. So when you're looking at this pattern, what happens is that with one single instruction, you can do an exchange like an any-to-any exchange, as long as you're not fetching from multiple sources. And so the way that the atomic instruction is written is that it's again the CUDA model where you're just describing the control flow of one thread. So a thread says, thread I says, I want to grab element blah, variable A, from thread J. So there's no need for atomicity in this case. All you're saying is that I want to get a value from element J. Yeah, I mean, if you have this thread and you have this thread, and you just want to exchange a variable from here to this guy, well, this will happen within a single instruction. So at that point, it's actually an atomic exchange. But yeah, I mean, given that this guy can do as much as it wants in the course of its life, it's up to you to ensure that the value that you're then fetching is the correct one at the time of the exchange. Yes, well, all threads call the same. Again, keep in mind, this happens all within the same warp. So you're executing your stuff in lockstep anyway, right? You have only, even though it touches on 32 threads, it's just one instruction that is being executed at the time. And so all these 32 threads come to the same shuffle instruction. And granted, given that each thread has its own state, each thread might be pulling data from another thread from different patterns. So the indexed any-to-any case happens fairly easily. Yes, yeah, that's true. So the benefit here is that it's not only that you're limiting, you don't need to have a synchronization between writing your data to shared memory and pulling it back out. The other benefit is also that you don't need any shared memory. And as you remember, shared memory is also one of those limited resources that is shared amongst all the threads that execute on a streaming multiprocessor. And so the not having to allocate, to set aside space in shared memory for just such an exchange can be very beneficial too. Right, so that's the extra benefit. Yes?
Now, am I guaranteed that, I mean, here I have to have some knowledge about which thread is in which walk, right?
Yes.
Right? So, am I guaranteed that 0 to 31 are in one walk, and
Yep.
32 to 63 are in the next one?
Actually, you're not guaranteed 0 to 31 are in one warp. You're guaranteed that 0 to some magic constant that you can query, which happens to be 32, are contiguous. But yes, I mean, up to warps, thread IDs are assigned in order to different warps. So yeah, 0 to 30, for all practical purposes, because we currently don't have a device that has that doesn't have a warp size of 32. It's 0 to 31, 32 to 63, and so on. Okay, and so here, just as an example for the benefit of the atomics, given that they are now so much faster, and what this allows you to do. Imagine you have an array of numbers, and you want to sum them all up. So if you look at early CUDA documentations, it was the poster child for selecting algorithms like a prefix sum for doing so. But basically what you need to do is, given that you cannot exchange information between different thread blocks, what you will do is that each thread block computes an intermediate sum, a partial sum. So they compute their sums independently. And then with another kernel launch, you're collecting all these results, summing them up, and create the final result. Now with atomics, so what this meant is that you have two kernel launches that are involved to get from the original vector all the way down to the total, the sum of all the elements. With atomics, you can get rid of that. You basically can compute the partial sums within a block, and then thread 0 of that block just does an atomic update in global memory of this of the sum, and we leave it to the hardware to make sure that you're not that you're getting the correct result, so that these updates of the global sum actually happen atomically. So this simplifies a lot of the You can have shared memory atomics, yes. So when you give shared memory when you give an atomic function a shared memory pointer, it will use a shared memory atomic. Now let me just try if I can get my laser pointer to work again. Otherwise, just tremendously handicapped if I... No! One more try. No. All right. Does anyone have the AAA batteries too? I'll come to... what would be this one? Another added feature of Kepler, and again, I'm sorry that this is a bit technical and we're probably not quite there yet. I just want to show you some of the nice benefits that we have, and feel free to ask questions afterwards what they really mean. But so far we haven't touched on textures, but again, that's something that comes out of the graphics world of the GPUs. When you think about it, you want to draw this monster on the screen. You have your triangulated surface. What you often need to do is then put textures onto this surface. And for that, we have a special data path that goes from the L2 cache into the streaming multiprocessor through this texturing unit. And what the texturing unit can do is it can quickly look up data in 2D space. It can even do interpolations for you, low precision interpolations, but so it has some particular smarts built in. Fantastic for some calculations. However, on the older architectures, it required that you had to go through a somewhat convoluted path to use this data path. Now, what happened with Kepler is that you have yet another data path from the L2 cache into the streaming multiprocessors that uses this read-only cache for the textures, but bypasses the actual texturing units. So you don't have the capability of doing interpolations in hardware, or that you have some, like the texturing unit can also do wraparounds for you and all kind of crazy stuff that in many scientific applications you don't really need. But what you really want to have is this additional cache. And so what Kepler allows you is with a single instruction, you can actually load data now through the texture cache into the streaming multiprocessor. And so this just gives you another path to load data. And for many applications, you will discover that you're actually limited by the memory bandwidth that you have. So how quickly you can get data into your streaming multiprocessors. And so fetching data through the texture cache can help you quite a bit there. So this is another nice added feature that allows you to reuse some of the data that you've previously loaded. Yes?
What's the bandwidth?
The bandwidth here is comparable to, so from the texture cache into the SM is we're talking about something like 600 gigabytes a second, or on 600 to 800, somewhere around there. The thing is that it's not only the fact that you have an additional cache, it's also that the, we come back to that later. No, I'm tempted to say now. So the thing is that if you go not through the texture cache, but through the regular data path, you want to make sure that adjacent threads load adjacent memory locations. Otherwise, if this is not the case, you actually end up having multiple transactions from memory to the SMs. And so you're just paying a huge penalty for access that's non-contiguous. The texture cache is organized in a different way, and it is actually designed for having non-contiguous memory accesses. So whenever you have scattered memory accesses, you probably should look into using the texture path, because that one is designed for data access patterns that are somewhat random. So it's not only the bandwidth, it's also the fact that you have higher dimensional locality in the texture cache as opposed to the regular data path. Okay. We touch on a few of these things later on in the optimization part. So this is pretty much what I wanted to say on the Kepler side. We're already way too far behind. Sorry for this rambling. Let's talk about optimization now. Yes? Right. It shouldn't anyone else. So it's basically those two threads. It is a function of the amount of the degree of the collision that you're generating, how much impact that the atomic operation will have. But yeah, the resolution of the atomics is actually, so first of all, we need to talk about which atomic operation we're talking about. The simplest is probably an atomic increment or an atomic add, right? Where you have a value and you want to add it to something that sits in global memory, and you want to make sure that two threads that add to this value, that there's no write after read condition. What happens is that when you're issuing this instruction, the actual increment operation doesn't happen, or the actual addition operation doesn't happen in the streaming multiprocessor, but it happens in part of the memory system. So we have compute logic way outside that does these atomic operations. So the impact of collisions will be out there, will be at the level of, will be resolved at the memory level, at the DRAM level, and not at the level of. I'm pretty sure it's going to be 32 bytes. Yeah. So pretty much all of our memory transactions happen at the 32 byte granularity. Yeah. Even though our cache lines are wider, but the smallest granularity is 32 bytes. Okay. Let's look a bit into optimization. This is to start with a bit less down to the technical level. However, I want to say it's there is a lot of information here, and I'm probably again having to hand wave a bit in between. But please ask questions if there is anything unclear. I'm trying to resolve, but yeah, maybe I need to point you forward to something later on. So first of all, some on of the fundamentals. In theory, optimization for GPUs is fairly straightforward. All you need to do is to make sure you have sufficient parallelism, and you want to make sure that all the execution units that you have are sufficiently utilized, and that you're not having too much divergence between the thread of execution. Those are the only principles that you have to look into. In addition, it's very useful to think about your memory system, that you really want to make sure that you're not using, that you're using the available memory bandwidth, so the width of the pipe between your memory and the processors, that you're using this as efficiently as possible. And here you're already seeing this fancy word, coalescence. Coalescence is what I described before, which means that you want to make sure that adjacent threads access adjacent memory locations. And again, the granularity of that is 32 bytes. And in the simplest form, you want to make sure that all 32 threads access 32 4-byte words that are consecutive in memory. But there is a lot of variety of different patterns that also give you perfect coalescence. Okay, now when you look at at how to approach this optimization part, it's good to have some kind of a systematic approach there, because otherwise you're just spending a lot of time and trying to fish in the dark what could be some way of optimizing your code, and yet you're just wasting your time. So it's good to have this some kind of strategy of how to approach the optimization, and we call this APOD, which is the cycle of assessing, parallelization, optimization, and deployment. So what does that mean? First, you want to have an assessment that is not just by staring at the code, but actually measuring where is my hotspot, where are the key bottlenecks in my application. And so you want to have tools like profilers and so on that help you identify these particular hotspots. What you also want to do is then to understand why those are the hotspots, which can be sometimes a bit tricky. And once you figured out which are the most important parts of your application, you want to get into the actual parallelization step. And yeah, we talked about the different approaches that we recommend there. And the next step is the optimization part. And even more important than in the assessment phase is in the optimization phase is to rely on tools. So don't try to just twiddle around lines of source code and hope that magically you'll find a better implementation. Use the profiler and figure out or learn from the profiler where the true bottleneck is. There's a variety of profilers available. In the CUDA tool chain, we have basically for people on the Windows side or people using IDEs like Eclipse, there we have nSight. nSight uses the same underlying technology as NVVP, which is our standalone visual profiler. And they're all sitting on top of NVProf, which is the command line tool that collects all the information about the application that you're running. So for an environment like 30, you probably want to use NVProf when running in batch mode, and then using on your workstation NVVP to analyze the profiles that you've captured. So this was the optimization part, and then the deployment part is basically just saying, don't try to create the optimal implementation at once, but rather push this out and see if maybe you're already there. Maybe the performance that you've achieved now is sufficient. At that point, stop. Don't try to over-optimize anything. Or alternatively, if you're still facing a bottleneck, go back to square one and restart with the assessment. So let's look a bit more in more detail into the assessment. We can later on look into actual profiles from the profiler, but basically what you get from the profiler is, and that's just very bad to read, but basically here you see a profile that tells you for the different functions how much time you're spending in those, and we have identified that there's this one kernel that uses a huge amount of the overall time. Oops. Now, the key now is to figure out how much time does this actually represent, right? Because you don't want to invest a lot of time in tuning something that eventually gives you a 5% speed up. Who cares, right? You want to go after these huge chunks that can give you whatever, these fantastic numbers that people have published previously about 100x speed up or whatnot, which frankly, nobody believes. I mean, the good thing about speed up is it's a relative measure. And so you can either tweak the numerator or the denominator. Oftentimes these huge numbers are just an indicator of a very poor reference implementation. Which shouldn't mean that you cannot expect great speed up with GPUs. I mean, we come to that later, but basically just based on the hardware, we have about 5 times the memory bandwidth as a CPU. So if you're memory bound, you can easily expect a factor of 5x. On the flop side, it's more like a 7x. So speed ups on the order of 5 to 7, maybe 10x, that's all within reason. But don't expect 100x. I mean, yes, you can observe it, but it's, as I said, it's probably more indication of a relatively poor CPU code. Right, so when you're assessing, you want to figure out how much time does this chunk represent that you're currently looking at. And the next thing you want to do is figuring out, well, what could I achieve? And that's, for instance, by just saying, okay, we're fantastic, we can get this time that it currently takes down to 0. And then you figure out how much speed up would that represent. And then from that you will infer how much overall improvement you can see. And we will go through these steps now in the following slides. So one thing that is very helpful to look at are both Amdahl's and Gustafson's law, which are for the strong and the weak scaling cases. And so for the strong scaling case, strong scaling meaning you have a fixed problem size and you throw more and more processors at it. how does the runtime behave? Well, Amdahl's law basically says that the speed up you can expect is 1 over the part which is parallelizable, P. Well, this one shrinks with the number of processors, N. And on top of that, you still have the time that it takes for the non-parallelizable part. Right, so you have a part that is, in an application, you have a part that can be parallelized and a part that cannot be parallelized. And the part that can be parallelized shrinks with the number of processors. The other one just remains constant. So in the limit, where you're going to an infinite number of processors, you're limited by your maximum speed up is 1 over the serial part. Does that make sense? Yes. Okay. Now, in the other case is where you're saying, I want to keep the amount of work constant per processor. And as I'm adding more and more processors, I'm growing my problem larger and larger. In the ideal case, your speed up as you go to more and more processors will just be n. Right? You're running on n times as many processors as an n times as large problem. It takes the same amount of time. Well, you have an nx speed up compared to the original one. However, this will be reduced by the part of the application that's non-parallelizable, because that one will just stay fixed. If you look at this case, well, it's easiest to understand if you look at the two extreme cases. The one case where everything is parallelizable, in this case, P is 1, so your speed up is n. Yes, that makes sense, right? You're just growing your problem as you add more processors, and you're still taking the same amount of time. Or the other extreme case is where nothing is parallelizable. So P is 0. At that point, S becomes 0. So your speed up is gone by the fact that you have nothing that can benefit from the fact that you're adding more and more processors. So now that we've identified in our code this piece that takes the most time, you want to understand it like, yeah, what is the scaling behavior of this function or of this part of my code? Does it more follow the Amdahl's law, or does it more follow Gustafson's? Are we actually, as we want to throw more processors at it, do we just want to make the overall time, the runtime shorter, or do we want to process more and more of the same at the same time? So in this particular case where we looked at this one routine I showed before, it was a fixed routine, for instance, a sparse matrix vector product. And we just want to take advantage of the GPU, so we want to throw more processors at it. So this is a typical case of strong scaling. And so we want to figure out what speed up can we expect. So if we assume that this kernel was using 93% of the overall runtime, which is actually a fairly good case, as we will see. So what is the speed up you can expect? Well, it's this, in the extreme case where we go to an infinite number of processors, it's 1 over 0 minus 93%, 1 over 93%, so 1 over 7%. That's something like 14x. And so that's sometimes helpful to just put this into perspective. Right? If you want to get a 100x speed up, this means that the one kernel that you're optimizing has to represent a huge chunk of the overall runtime. And so for those of you who have actually looked into a profile of your application, I mean, how often do you see an application where you're spending 99% of your runtime in one single function or in a few functions? I mean, that's hardly ever the case. Especially when you're looking into real-world applications like a weather forecast model or something like that, you're just looking at these ugly flat profiles where each function takes 5% of the time, 10% of the time. So that's when you want to have tools like OpenACC, because you're looking at a lot of code that needs to be moved onto GPUs. Because yeah, if a routine just takes 10% of the time, well, the maximum speed up you can get from that is how much? I would need to do the math. It's 1 over 1 minus 0.1, so it's 1 over 0.9. It's like 1.2 or something like that. I mean, it's nothing spectacular. So, yeah, you really want to look at these very large parts of the code, these huge poles in the profile. And then so that's assuming that you had an infinite number of processors and completely ignoring any kind of hardware or limitations that you might have. Then to refine this a bit more, so instead of hoping for a factor of 14x speed up, you want to figure out like what is currently limiting, what is limiting us? Why aren't we seeing this 14x speed up compared to or why aren't we seeing the slower runtime? And for that, you need to guesstimate a bit. I mean, are we limited by the memory bandwidth? So are we limited by the speed at which we can load data into our streaming multiprocessors? Or are we really limited by the number of floating point operations that we can perform? A typical example here is dense linear algebra. Right? You probably learned in some of the computer science classes, if you want to do a matrix-matrix product, that this is an order n cubed operation. Okay? So you have an order n cubed floating point operations, and yet you're operating on order n squared data elements. So you would expect that you're basically limited by floating point operations because you're for a given size, right? Because you're scaling with n cubed as opposed to the n squared. Well, that is true once n becomes sizably large. But that's the problem about the big O notation, is that there is constants involved. And you can always find the case when you're going to very small matrices. Well, you still have order n cubed operations, and yet you're not as quickly loading your data as you can process them, because we have a slight imbalance between the amount of data, or the speed at which we can load the data into the processors and the speed at which we can process them. And so even for dense linear algebra, you're ending up in situations where you're limited by the memory bandwidth as opposed to the speed at which you're computing. And then there's a third category that you can run into, which is just latency. And this one is sometimes a bit hard to discover and to figure out. But remember the graph I had at the very beginning with the showing how we do latency hiding on the GPU. So we have, it takes a certain amount of time until we fetch our data, and if we have sufficient work, then all this latency is hidden with useful work. Well, in cases where you don't have additional work to perform, you will be exposed to all this waiting time until the data has arrived. And so in those situations, the only thing you can try to do is to make sure that you're having few enough operations that access these very expensive global memory elements. And that's now all fairly hand-wavy, but we get to some harder numbers later on. So yeah, to come back to the dense linear algebra case, it's sometimes useful to just look at the ratio between the amount of floating point operations you perform and the amount of data that you need. That's usually referred to as the compute intensity. So you're just looking at the number of bytes versus the number of flops. And so for us, in order to be compute dominated, you want to have a ratio that's probably on the order of 5, 6-ish. Whereas for truly memory bandwidth limited cases, like stencil calculations, you're usually on the order of a few, 0.2, 0.3, 1. So when you're computing this ratio, just see if you're more on the low end of the spectrum or on the very high end. Okay. So I think we've covered this one. Yes. And now, again, the beauty is that our tools offer insight into all this information based on measurements. So with the profiler, you actually get some very nice graphs that show you like how much time you're spending on the compute side and how much time you're spending in accessing memory. And so this is a fairly nasty case where you have both of them are kind of the same height, right? So compute and memory. So this is typically a case where you need to reduce the overall latency of your operations, of your kernel. In some cases, you just see that most of the time is spent on the L2 side or on the memory side, or most of the time is spent in the compute side, and then you know again which part to focus on. Yes, we talked about the speed of light considerations. Again, once you know what the most limiting factor is, you can estimate what performance you could possibly achieve. Right? If you know that you're limited by memory bandwidth, well, then you just say, okay, let's assume that I'm not computing anything at all. How much time does it cost me to move this chunk of memory to my streaming multiprocessors and from the streaming multiprocessor back to memory? That's a fairly simple calculation you can do. And that tells you what the speed of light of your operation would be. Whether you can achieve it or not is a different question. But at least you get an upper bound or a lower bound for the overall time that you can expect. Okay. So we talked about the assessment. Again, you have your kernel. You figured out or you have your application, you figured out what is the hotspot. You figured out what the limiting factor is. So now the question is, how do you resolve that? What kind of changes can you make to your code to get rid of a performance bottleneck? And so let's first look at at computation. We're just circling back to the same slide over and over again. For parallelization, just pick whatever is the simplest possible approach for your problem. If it's something that is packaged in a library, just use it. There is no reason to re-implement a prefix scan operation. There's tons of libraries out there. In the worst case, just grab from the web some code and cut and paste it. But yeah, don't spend your brains on re-implementing a parallel scan. Or if you can actually use OpenACC, use it. That's and as you know, since we introduced at supercomputing, there's going to be GCC support for OpenACC coming next year. So you're even no longer locked into a commercial compiler when you're using OpenACC. Or then, use CUDA or CUDA Fortran, depending on what your preferences are. Oops. I'll spend some more time later on the. Let's on the library. I'll talk a bit more later on. But the one interesting part for the C++ programmers here is Thrust, which is a library that's fairly close to STL. It's designed after principles of STL, so the standard template library. but it has a lot of interesting features that make life much, oops, get out. Sorry. That make it much easier to write parallel code for the GPU, especially when you need things like sorting or other algorithms like reduction algorithms. Thrust has them already built in, so it can be a very high productivity approach to writing parallel code if you're in the C++ world. The other benefit is that it also supports different backends. So you're not limiting yourself to CUDA, but it can also target OpenMP or the TVB, so the thread building blocks. So it's a fairly generic tool. It's not officially part of the CUDA toolkit. It's being distributed with the CUDA toolkit, but it has its own release cycles. So the CUDA toolkit tries to be on a biannual cycle, and so twice a year. Is that biannual? Yeah, and Thrust can be released at a higher frequency. So we're not coupled there. OpenACC you have talked about a lot, and we looked into CUDA code. So, right, I think here we talked about the massive amount of resources we have, the parallel resources on the chip. The second bullet, I think, is an important one, right? So we want to have a large degree of parallelism, not only to fill all the available pipelines that we have, but also to hide all the different latencies, for instance, for grabbing memory access or grabbing data from memory, or to hide the latency of an operation, right? And a floating point operation is not happening within a single clock tick. It happens, we come back to it later, but roughly 10 clock ticks for a usual operation. So just as a rule of thumb, on a K20X, you probably want to have something like 14,000 threads on average, to be on the safe side, to have a good utilization of your device. Right, I mentioned this morning that a K20 can track up to about 28,000 threads at any given time. So it's not necessary to use all of them to really utilize the device efficiently. But yeah, you still want to have a massive number of independent threads that can be processed at the same time. So that's why it's always easy to use GPUs and see good speed up for large problems. It gets sometimes a bit hairy when you're attacking small problems. Anything that's small is not particularly well suited, and that's where a true hybrid approach comes into play, where you're using the latency optimized processor, the CPU, for the small problems, and you're using the GPU, the throughput optimized, for the large problems. Yes? So far, there's no kind of a unified scheduler on the hardware side that does that. Now, there's various research efforts that have been looking into exactly that. Right, one of the challenges you're facing there is the question of what do you do with the data locality? If you have multiple steps in a processing pipeline, well, it could be that for whatever reason, a chunk of data needed to be on the GPU for the first step because it made sense to have it on the GPU. Now, if a small piece of work comes along, is it really worthwhile to then lift the data up from the GPU to the CPU just to run the small thing there? Or does it make more sense to abuse the GPU to some degree, inefficiently use the GPU with a small piece of work, but it saves you the data transfer time? So those are what seems to be fairly simple turns out to be a fairly nasty problem, and there are efforts like a scheduling system called StarPU that does exactly that. I mean, you can tell it some scheduling heuristics. You're basically providing for each function both a CPU version and a GPU version, and it will then at runtime juggle around and figure out what to do with the which resource to choose for the particular work that you have at hand. Fairly interesting research, but it's still researchy. Okay. Oops. So also the hands-on example that we do later on will all be around. Oops. No battery. Okay. Will all be about matrix transpose. Which seems a bit annoying that you have to spend so much time on something as simple as transposing a matrix, but it's just a good use case because we can illustrate a few of the core concepts on it. So when you want to transpose a matrix, the way you would write it on the CPU is basically as follows, right? You have your in matrix, and we do column major. Right? Is that true? Yeah. So the J's are contiguous in memory, and the I's are strided. Always difficulty between flipping on between Fortran and the C phrasing, but in any way, so you're seeing the problem here is that irrespective of in which order you're keeping it, you always end up either in one case you have contiguous memory access, and then in the other case you're either reading contiguous memory and writing discontinuous memory, or you're reading discontiguous memory and writing contiguous memory. But yeah, in the simplest form, it's just a doubly nested loop. So if you want to move this to a GPU, what do you want to do? Well, the simplest form to do that is just take the code that you have on the CPU, throw in a global at the beginning of the function, and launch this kernel with a single thread block and a single thread. Performance is obviously not fantastic, but you're done within minutes. Now, obviously what we didn't do is we didn't do any parallelization. But it can actually sometimes make sense to do something in this way, simply because, right, initialization routines. For whatever reason, it might be necessary to move data first onto the GPU to have it allocated there or initialized there. And then you need some pre-processing to be done. Well, if it's a hard routine, or if it's something that has a lot of dependencies and so on, yeah, based on your profile, you'll probably find out that it's such a small part of the overall runtime, you might as well afford to just do a crappy job in that. That's always a possibility too. Yes?
This is definitely going to be a lot slower, right?
Yes, right. I mean, compared to a CPU, definitely, right? Because we're running at a fairly low clock rate. Our core clock is on the order of 800 megahertz. If you compare that to whatever a 2.5 or 3 gigahertz processor, yeah, you will just lose out there. And then, yeah, we don't have the deep cache hierarchy and so on and so forth. So yes, this will not perform well, but it's quickly implemented. No, and I mean it comes across as a joke, but that's actually an important point, is that you want to focus your efforts on the parts that actually make sense, that you don't want to waste time on an initialization routine. And if it's just, yeah, if it's something that happens once, well, yeah, just get it onto the GPU and let it run there, even if it's not optimal performing. The goal is that you have this cycle of refinement, right? If you then start to care about it, at one point, maybe this initialization routine becomes the bottleneck, and at that point, you need to attack it. But you shouldn't need to attack pieces of code that are basically, from a performance point of view, irrelevant. You want to have this path of an iterative refinement that allows you to terminate when you run out of steam or out of funding or whatnot for doing this particular job. Right? The worst situation that can happen is that you're spending 3 years of your time or 3 years of funds, and you're building code, and at the end you have nothing. So what you want to be in this situation is that you always have something running. It might not be optimal, but you can, one after the other, attack these individual bits and pieces that need to be refined. So what you rather want to do, instead of just having this single, this straightforward approach, is that you want to parallelize across the elements. We're doing an out-of-place transpose, right? We have the input and the output matrix as two separate ones. Well, each element can be completely independently transposed from each other. So in this case, you probably want to use something like n by n threads altogether to process an n by n matrix. And that's exactly what we do here, right? We're launching n blocks, each block with n elements, each block with n threads. And now, for simplicity, we assume that n is a nice number, whatever, a multiple of 32. And so what you're ending up with is that in your transpose kernel, all you need to do is figure out what is my thread ID, what is my block ID, and the index calculation then becomes relatively straightforward. So for the input side, you're having the thread ID gives you the contiguous offset, and the block gives you the individual rows. And for the output, the block gives you the contiguous index, and the threads give you the individual columns in that case. So here we have a kernel that does all the elements entirely independently and transposes them independently. Now, whether this is a good implementation or not still remains to be seen. It's definitely going to be better than the implementation we had before, because now we use quite a few more threads than we had in the previous case, so that's good. However, as you remember, we should be careful about memory access patterns, and as you can see there, in one case we have a huge stride between adjacent threads accessing memory, and in the other case we don't. So this could be a problem. But from a parallelization point of view, we've done our job. Now, what I've talked about so far was the parallelization at the level of for compute, so within the streaming multiprocessor. Now, there's another level of parallelization that you can exploit, which is the data transfer between host and GPUs. Remember, we have the host side, the blue, and we do DMA, so memory transfers to the GPU, and we need to transfer this data back. Again, when you're familiar with MPI programming, these are your send and receives between host and GPU. And what you learned quite early with MPI is that you want to be able to overlap all these communication with some computation, and that's here exactly the same. You want to be sure that you have sufficient work to overlap these data transfers with something useful you can do. And so that's asynchronicity of kernel execution and data transfers. The GPU supports that. I think I mentioned that this morning, that by default, CUDA memcopy, for instance, is blocking. And so it's synchronous. But there is mechanisms of getting them to execute at the same time. Now, this works now. So here we just have a screenshot from the profiler. And what we can see here on the left-hand side is basically activity. The blue one is activity on the GPU. So those are kernels that are being executed. And the brown ones are data transfers. So you see we and it's probably hard for you to read, but this one says memcopy H2D, so host to device. And down here we have memcopy device to host. So basically we ship data from the host to the device, we perform the kernel, and we ship data back. So this is time, and these are different operations. And then later on, we do, again, copy from host to device, perform the operation, and back. So when you look at the GPU, I mean, even though we have constantly something going on, when you look at the GPU, this is just this particular part here. And you see that the GPU is basically idle most of the time. There's lots of wide gaps here. So what you want to do is you want to make sure that these brown blocks, the data transfers, overlap with actual computation. So this is the picture that you would like to see, right? Here we have a host-to-device transfer, then we kick off a kernel, then we have another host-to-device transfer that happens while this one kernel is processing, and we have yet another host-to-device transfer, and we at the same time even do a transfer from device to host. So we can do concurrent transfers in one direction and the other direction. Hi. Sorry. Where do I set my status? Probably just do a quit. Sorry for that one. Yes, quit. So here we have basically gotten maximum overlap of data transfers in both directions and the kernels that execute on the GPU. So this is the picture that you want to have at the end. The mechanism for getting there, we'll talk about tomorrow. That's streams. So it just takes a little bit more work, but it's definitely something that you want to look into. If you see that your operation is pretty much a pipeline, so you're moving stuff from the GPU to the from the host to the GPU, process and get it back. Think about ways of overlapping these transfers. Okay, optimization. And yeah, I guess we're pretty soon approaching the saturation level. I've talked way too much, but let's just briefly look a bit into some of the steps that that we can do for optimization, like in case of the of the transpose. So first of all, there's this guide called the CUDA C Best Practice Guide. And that's very helpful in terms of giving you some recipes of how to go through a code and look for individual bits and pieces that you could optimize. As you can see here, there's a whole laundry list of different things like, how to parallelize, doesn't really help. Kernel launch configuration, right? The question of, do I rather want to have large thread blocks, well, with many threads, but a few of them? Or would you rather have more thread blocks with fewer threads? What is the best solution there? Well, it depends. Memory access coalescence, getting rid of memory accesses, avoiding thread divergence. So that's all a lot of different bits and pieces. The good thing about the best practice guides is that it gives you some information about how relevant these different optimizations are, right? You shouldn't try to optimize for instruction throughput when you're still having huge problems with memory coalescence. So the guide gives you some weighting and says, look, this is a high priority optimization, this is a lower priority optimization. So the next, what I would like to do today, some of the optimization we will cover tomorrow, but what I'd like to do today is look a bit more into the kernel launch configurations. Yes? And actually, that's what we're doing now. That's so that's the kernel launch configuration optimizations. Okay. Right. So this is exactly this question. We have a grid, and we have a certain number of threads per block. What is the best choice? And the buzzword there is the so-called occupancy, or warp occupancy. Because basically what it all boils down to is that you want to have sufficient work available at any given time, that whenever there's an operation that the GPU needs to do that takes a certain amount of time, that has a certain latency, that there's more work to hide that latency. And so the question is, how do you get sufficient work to the SMs? So it makes sense to look at the streaming multiprocessor. This is just as a reminder of all the different technical data points. I'm sure you still remember them from this morning. And the thread execution model, again, it's right. You have a thread, they're grouped into thread blocks, you have multiple thread blocks that execute concurrently. And one of the things is, we have multiple thread blocks that execute across multiple streaming multiprocessors, but you can also have multiple thread blocks executing concurrently on the same streaming multiprocessor. And that's all dependent on the available, or on the architecture, right, where you have the multiprocessor is basically responsible for one or multiple thread blocks, and the multiple multiprocessors are responsible for the entire grid. So maybe just start with a few rules of thumb. You probably want to start driving by the number of thread blocks. You always want to have something like 1,000, multiple thousands of thread blocks that can be launched. How does that come, or why? So a streaming multiprocessor has a certain number of hardware limits. One of them is that an SM can at most keep track of 16 thread blocks at any given time. Okay, we said it can keep track of 2,048 threads, or 64 warps, or 16 blocks. Now you can do the math, and it turns out that this corresponds to, in case you have 128 threads, you're satisfying 128 threads per block. You're satisfying all these constraints, right? Because 128. So let's see, am I getting this right? 128. That's 4 warps. That's 4 times 32. And times 16. 4 times 16 is 64. Yes, right. And so we can. That means we have 4 times 16, 64 warps, and that's exactly the maximum number of warps that we can keep track of on an SM. If I had a whiteboard, I could write this down, but that's a big if. I'm happy to. Maybe later on in the break we can come to that. But it boils down to this consideration, right? In the simplest case, you have 128 threads, 16 blocks, 128 threads per block, 16 blocks per SM. Now, 16 blocks per SM times 14 SMs per GPU. So you want to have 16 times 14, that's 700 something. So just to fill your device, just if you want to use all the available resources, you want to have at least 700 thread blocks at any given time on your device. So, and the better, the more the better. So as a lower number of thread blocks that you want to use, 1,000 is probably about right. Now this was too many numbers that I just threw at you. Sorry for that. I hope we can come back to that in the following of these. So, but for now, just assume, let's say 1,000 blocks per GPU is kind of a reasonable number. And again, the number of threads per block, you don't want to go much below 128. Why? Well, if you have fewer threads, you're running into the situation that you will not have sufficient warps available at any given time, so that you can run into the situation where the SM basically has to idle because there is simply no work to do. As I, in a convoluted way, calculated for you before, 128 is an ideal number. In some cases, it makes sense to increase it a bit. Yeah, it depends again on the balance of the resources, and we come to this in a second. So the other consideration here is you definitely want to have a multiple of 32s, because if you're not having a multiple of 32s, well, the hardware will still run at multiples of 32s. So you just have a bunch of threads that are idling, so you might as well use them. And yeah, this down here, pick the number of threads per block that keeps the SM busy. That can sometimes be somewhat of a black art to figure that out. Yes?
Can I ask you the inverse question?
Yes. So I assume you're saying 10,000 by 10,000, or? Okay. Well, so the reason I'm asking is 10,000 is already kind of a nasty number, because it's, remember we had the, I said something like 14,000 independent threads you want to have. So it puts you somewhere at the lower end of those. So let's assume 100,000 or 1,000,000 elements, right? Just to be on the safe side. Well, so what is matrix transpose? And I'm assuming we're doing a matrix transpose in those, right? Well, let's assume matrix transpose. Okay, matrix transpose, gut feeling, is that compute bound or memory bandwidth bound? Bandwidth, yeah. I mean, you're not computing anything. You're just moving data around. So all that matters is the bandwidth. Okay. Now, in order to fully utilize our bandwidth, you want to have as many. Well, there's nothing to hide the memory access latencies. There is no compute that you can do. So you want to have as many threads as possible that could grab data. Okay, and so you want to have your 2,048 threads per streaming multiprocessor. This will give you the optimal bandwidth. So now the question is, how do you get these 2,048 threads? What other, are there any other factors that will tell you how to break this up into your thread blocks? And I mean, you just want to have a single thread block, and 2048 threads would be a possibility. However, in your transpose, you probably need to do a little bit more than just suck in data and write out data. Right? There's most likely the way you're doing it is you read the data in, you put it into shared memory, you have a barrier, because you want to make sure that all your data is in shared memory that you need to write out, and then you're writing it out from shared memory. So this barrier makes it a little bit tricky, because that means that you have to make sure that you have sufficient threads to, you're not blocking any of the threads at this barrier, and therefore expose yourself to the full memory access latency. Right, that you end up in a situation where n-1 threads are sitting at the barrier and waiting, and you're just having this very last thread, or this last warp, that just needs to wait all the way for getting this data out. So you usually want to avoid having a very large thread block, especially when you have synchronizations in between. So you look at the other extreme. What is the maximum? You could have just a single warp. Now the problem there would be that you're ending up with, you're ending up with a maximum of 64 warps that you can, in theory, you could have 64 warps that run on the device. However, 64, if you had a single warp per block, this would mean you would have 64 blocks on the device. The device cannot hold that. The device can at most hold 16 blocks. So of all the 64 warps that you could possibly schedule on the device, you can only use 16 because you're exceeding the maximum number of thread blocks. So you're underutilizing the device. Now, this would be in case where you're just using a single thread block. If you're using, if you're using a single warp per thread block. If you're now using 4 warps per thread block, okay? So, 4 warps per thread block. Four warps per thread block. 16 thread blocks can be held on the device. So that's 16 times 4. That gives us 64 warps that can possibly be on the device. This gives us the maximum number that the device can hold. So we're maxing out the number of blocks that we can have. That means the maximum number of independents. We have the maximum number of warps. So chances are high that the number of 4 warps, 16 blocks per SM would be the right choice. So long story short, and I probably should have started with the answer, I would start with 128 threads per block, and as many blocks as you need. By the way, if you're using Cray's OpenACC compiler, default choice is 128 threads per block. And there will be a picture later on about the occupancy calculator. Yeah. Yes, so we talked already way too much about the warps. And yes?
I still have a question.
Okay. Yeah, oh, sure. You're not the only one.
Another extreme case, say you
Yeah.
have not just say 100,000 elements to run the process, where you just say, okay, each iteration is 1 thread, but you have billions. Is it then better to really span billions of threads, or should every thread have some inner loop that processes some of these elements as its own?
So it depends a bit on how much work you're doing per element. Right? The first cut would be just use a single element per thread. So and use as many threads as you need to cover your overall array. The slightly better answer, or what in reality will turn out, is the fact that you need to do address calculations, right? So again, we used a very simplistic case of just doing a vector add. We have a sub I plus b sub I is c sub I. So that's the operation we do, okay? Now, in order to do this operation, we still have to, each thread has to do the integer arithmetic for figuring out, like, what is my I? Remember this expression we had for, like, thread ID plus block dim times block index. So each thread has to do this operation. And, yeah, and possibly some additional operation depending on how exactly you're accessing this data. So you're not only moving data from global memory to your processor and spit it back out, or do a little bit of processing and spit it back out. You actually have to do quite a bit of processing for just getting the address is right. So you might be better off in doing multiple elements within a thread just to compensate for the costs that you're introducing for doing this, this address calculation. So the approach I would take there is start out with using a single element per thread. Look in the profiler, check what bandwidth do you get. And then see how, I mean, at that point you might figure out what the cost is, the relative cost of the index calculation compared to the calculation you're actually doing on the device. And then based on those values, decide whether you want to go forward and process multiple elements. And actually the exercise on the transpose does exactly that. So as we will see is, yeah, so as we do the refinements in the transpose, at one point we see that we get the best performance at the end where we're processing multiple elements per thread. Okay. So we talked a lot about the warps and like how many warps we could have running on a streaming multiprocessor, and the buzzword there is the occupancy, which says out of those 64 warps that possibly could be on the streaming multiprocessor, how many do we have running at any given time? And again, the profiler gives us a nice number. It actually will tell us what the theoretical occupancy is. The theoretical one is defined by looking at all the limiting factors that we have. I said we have a limit on the number of thread blocks that we can have per SM, 16. We have a limit of the maximum number of warps that can be on an SM. That's the 64. We have a limit of the number of registers that each one of the threads can use because we have a finite register file. If one of the threads uses a huge number of registers, well, we can't put as many threads onto this SM as we want. So register utilization can limit your occupancy. And finally, the amount of shared memory that each one of the blocks uses can limit your occupancy. So you can come up with this theoretical number based on all these limiting factors. That's what the theoretical occupancy is. Here it would be 100%. In many cases, even the theoretical occupancy is actually much lower than that. And the achieved occupancy is then basically measuring how many warps were actually being executed. And that one can oftentimes be slightly lower. It's usually fairly well limited by the theoretical one. So when you, yeah. So again, just why do we care about this occupancy? Right? This basically tells us if we have a warp here and it has to wait for a long time, do we have sufficient work to cover all the latencies that are being introduced? For instance, due to accessing global memory. And if we don't have sufficient work, for instance, if we only had warp 1 and 2 available on this SM, well, we wouldn't be able to fill this gap, and we would have this huge white box where the GPU is just sitting there and idling. And that's what we want to avoid. And so as I promised before, there are some numbers of like, what are these latencies? I've always used the global memory access latency. And as you can see here, this is also one of the largest ones. I mean, we're talking here about something like close to 1,000 cycles that it takes for just getting data back from global memory. So when a thread says, I want to access variable A that currently sits in global memory, it takes 800 or 500 cycles to get this, this result back. So you definitely want to have more work to do during this time instead of just waiting. But memory access is only one source of latency. There's also just arithmetic operations that takes on the order of some 10 to 20 cycles. right? And so you want to have sufficient work that whenever you have an operation like this that takes so long that you can hide everything that happens in between. Right. Right. And what is written down here is just that the way that we're set up, don't think of it as a similar on the CPU where when you're switching between one thread to another that we have to do an actual context switch. This is not the case. We have a fixed register file of a certain size, and we have so whenever one instruction has been issued, the scheduler can pick pretty much an arbitrary other instruction to execute without an extra penalty. So out of these 64 possible warps that we have, it can just pick whichever is ready and issue that instruction next. Right. We come back to the famous or infamous occupancy. And here is just once more listed the limiters, what can limit the number of warps that you have executing on the SM. So one of them is just the number of threads in a thread block. And then the registers and the amount of shared memory that we use. And over here you have, again, the list of these resources. As a rule of thumb, for registers, the number of registers is not becoming a limiter for you if you're using less than 32 registers per thread. Anytime you go beyond 32 registers per thread, you run into the danger that it becomes a limiter. But yeah, you're now wondering, how can I influence that, how many registers I'm using? We come to that tomorrow. But it's probably one of the most likely limiters that you're running into. The other one is shared memory. 48 kilobytes is not a whole lot. Again, if you want to have maximum occupancy, if you want to use all 16 all slots that are available for the 16 blocks that you have, this means a maximum of 3 kilobytes per block. Right? So a maximum of 3 kilobytes of shared memory per thread block. So, yeah, as long as you're using 128 threads per block, 3 kilobytes of shared memory per thread per block, a maximum of 32 registers per thread, you're totally fine. You don't have to worry about occupancy. As soon as you're using one of those resources a bit more extensively, then yeah, you might need to twiddle a bit there. Now, one thing to keep in mind is what I've said before was always assuming that you want to achieve 100% occupancy. Now, it's not necessary to have 100% occupancy. Oftentimes, once you're getting beyond something like 60% or so, you're fairly safe. What you will see is that you can spend a lot of time of getting your resource consumption down, and you won't see any speed up. That's simply because you're no longer limited by the available by the occupancy that you have available. So yeah, again, as a rule of thumb, once you're beyond about 60% occupancy, you're most likely fine. I want to skip over this one. We just go straight to the pictures. I've drawn this one in the air several times before, but what you see here is basically the number of the number of warps that are allowed by the SM. So again, we said 64 warps is the maximum that any SM can hold. So if you're right, if you're using too few threads, that was the situation where I said we just use 32 threads per block. Well, we can have a maximum of our 16 blocks. Well, this will limit us in the amount of the total amount of warps that we can use. So that's not good. Or the other one is the case where we're using too many threads, and so we are, again, limiting the number of blocks that can execute at the same time on the SM. So once more, you're running into the situation that you're not getting as many warps onto the SM as you should, or as you could, I should say. Now, this was bad. Anyway, so this was the picture I wanted to get to. There is this Excel sheet called the Occupancy Calculator, and that helps you to kind of navigate these different balances of the different resources. So what you see here is there's basically just 3 inputs that you need to specify. You need to specify how many threads that you have per block, how many registers you're using per thread, and how much shared memory that you're using. And so the occupancy calculator will then tell you like what the occupancy is, the theoretical, based on these limits. And it will tell you, like it gives you some feeling of like how many more registers would I need to use, or how many registers less I would need to use in order to get higher occupancy, or how much more shared memory could I use. So for all these questions about the trade-off between how many threads I want to have per block, how many blocks in total, the occupancy calculator can be a fantastic tool. And yeah, we probably should go through that at one point later on in the hands-on. But for now, I would say yes.